Thank you, Rowena, I think, for that invitation, that introduction. So I'm going to talk about some of the fun stuff, what we're actually doing in the clinic now to actually cure people. And I'm going to go through the greatest hits of cure interventions. There have been several attempts. And the take-home message is that we are now at that point where we're actually ready to do all these proof of concept probe studies, okay, where we actually take an idea from the lab that was discussed this morning and move it into the clinic and do the first in human type studies. These are high risk studies, they're complicated studies. They often don't necessarily give us an answer, they often give us more questions. But that's where the field is. And there are dozens of these studies now that are happening or about to happen throughout the world. And you're going to hear about them as we move forward. As you will see, in general, what we have found is that every time you do these types of studies, you make some advance, people get excited, you go and try to do it again, or you look a little bit deeper, and you come back a bit. So 2 steps forward, 1 step back. And that's basically the outline here of this presentation. 2 types of cures that we think about. It's a bit artificial. One is the so-called functional cure. This is one in which we do not try to eliminate the virus completely. I think Rowena talked about this morning. We assume that the virus will persist, and what we want to do is get that viral load down so low, probably less than 100 copies in the entire body, that the immune system could take over and control the virus indefinitely. And there's optimism that we can do this because actually one in about 100 people do this on their own. We have people in our clinic who were infected in the late 1970s. It's over 30 years now. They basically meet any definition of having been cured, in large part because their immune system is able to control the virus. But the virus is there. That's a functional cure. And then there is a so-called sterilizing cure, and we clearly need a better name for this approach. But this is the ultimate goal. This is where somehow, with some intervention, we go in and we completely remove all HIV. A lot of very smart people do not believe that it's actually possible to do this, and that we will actually ultimately need to have more of a functional cure. My personal opinion is that we need both. You are not going to cure someone, I don't think, functionally, if there's a lot of virus left. So we have to get rid of as much virus as possible, then let the immune system take over. We're not going to truly sterilize people very easily in terms of their HIV. We're not going to limit everything, so you're going to actually need a functional part of it to contribute to this side. So these things go hand in hand. All right, so how are we doing this in the clinic? So there are several ways. First, to prevent latency with very early antiretroviral drugs. There's been some success, some failures. So-called shock and kill, where you actually go into a person, you find the latent reservoir, you shock it with some kind of drug, you get the virus out, and then you kill it. That's shock and kill. There's a lot of interest in modifying the host environment to make it a bit harsher so the virus can't replicate. And of course, there's gene and cell therapy. So, can we cure HIV with very early therapy? And I think the answer is certainly yes. It gets kind of into how you define things, but we now know that you can, if you give antiretroviral drugs to a person before they're exposed, Truvada for PrEP, you can actually prevent people from becoming infected. It works quite well. We do know that if someone is exposed and presumably has a little virus somewhere, if you give antiretroviral drugs within 24 hours, we call this PEP, post-exposure prophylaxis, you can prevent infection. To a certain degree, you're actually curing them at the same time because they have virus there. And the question really becomes, after PEP, within 24 hours of exposure, at what point in time can we give antiretroviral drugs to a person who has HIV such that you prevent the long-term establishment of the reservoir? All right, so that's a question that's actually out there. It was probably most eloquently posed by the so-called Mississippi baby that you heard about. This is a baby, an infant born in Mississippi, who had a viral load that was quite high at the time she was born. But the pediatrician just slammed her with antiretroviral drugs, 3 drugs right up front, at hour 31 of life. And the viral load disappeared in the blood, and the baby stayed on therapy for about 1.5 years, and then for complicated reasons, the mom disappeared, and the baby stopped taking drugs. And then the baby returned to the clinic and is now a young kid and had been off antiretroviral drugs and was HIV negative, didn't have any antibodies, and basically did quite well for a couple years. And then the virus rebounded. So prior to this, we had thought that the baby had been cured. And it's the same case with the Boston patients, right? Apparently that was not true. The baby had a little bit of virus around somewhere. But what did the drugs actually do here? The drugs are doing here is they're actually probably, in my opinion, and this is the focus of a lot of research, a lot of it funded by amfAR, what I think is happening now is if you can actually get drugs into a person really early, you can prevent the establishment of latency. Latency, this issue of actually having a virus live in a long-lived reservoir, is actually not that easy for the virus to do. It's a complicated process. It takes a fair amount of luck. So there's a lot of thinking that we can actually get drugs in soon enough to prevent that inefficient process from happening. But how about adults? So here's a study that amfAR has recently funded that's happening in the San Francisco. We're taking very high-risk gay men who have lots and lots of exposures, who are going to go on PrEP, Truvada, right, to prevent them from becoming infected. We have found actually that not infrequently, some of these guys are having so many exposures that at the time they show up to start PrEP, they have just now become infected. And we have a couple now who on the day they started Truvada for prevention, it turned out that they'd just been infected for a few days. So they're actually starting therapy by luck right at the earliest possible phase to start antiretroviral drugs, just as the virus is becoming indetectable. And we have found actually when we do this, we actually have now a couple of these guys who've been on therapy for a year and a half, and we just cannot find virus anywhere. Clearly the virus there at the beginning, but not enough was established, we hope, so the person had long-term infection. And we're sending blood to Tim to inject in his mice to see if that virus will rebound. And we haven't done that yet, but as soon as we do that, and we're doing all sorts of other work with a bunch of other collaborators, much of it funded through the ARCH network, which is actually a very virtual network these days all around the world. We're sending blood from this patient to everyone who might have an ability to tell us, does he actually have the virus? So far, no one's found it. And ultimately, we're going to have to stop drugs. And we will do that hopefully in the next several months. So that's early antiretroviral drugs. That's not going to change the world, right? Most people have the virus. Most people who get the virus have no way to get on therapy until the virus is fully established. So what are we going to do about those people? 35 million people around the world who actually already have the virus, and of course millions in the future will have it. Most of the interest is in shock and kill. All right. And that is basically this concept that you take a T cell, it's got the virus in it, you shock it, you blast it, you turn it on, virus comes out, you turn on the immune system, you kill the virus. Okay? Kill the T cell. That is the plan. It sounds straightforward, very simple. Can it work? Well, the shock part, the first real solid evidence, I think, consistent that the world has accepted as true, that you can actually shock the virus out, came from this study that Lars will speak about later on this afternoon, his team in Denmark, where they took a drug called an Htac inhibitor, that's a cancer drug, that untangles the DNA in such a way that the virus DNA becomes exposed, and then it becomes turned on, and the virus is made. And what they found is that if you gave a dose of this drug, romidepsin, the amount of virus in the blood went up just a little bit, came back, I don't know, a week later, gave another dose, and boom, you had this spike in virus. Did it again, another spike, at least in one person. Okay? Proof. You can do this. Now, these people are not being cured. The reservoir size has not really changed. This is just the tip of the iceberg. But it's a really important proof that you can actually truly shock the virus out. Now, these patients are all on antiretroviral drugs, so that when the virus comes out, the antiretroviral drugs blocks it from spreading. All right? And we hope that these cells making the virus are dying away, but we don't really know that yet. A bit more controversial, but perhaps with a more power to be generalizable through a study that has been entirely supported by amfAR going back years from a discussion I had at an amfAR meeting here in New York with Bob Silicano. We've been working on this concept disulfiram. Disulfiram is antabuse. If this works, it would be a beautiful drug because it's been around for decades. It can be given for years and years. It's very, very safe. And in a pilot study that was funded by amfAR, we found that with disulfiram, antabuse, which really has no toxicity if you don't drink, it's a separate discussion, that at least in a couple people, by surprise, there was this rapid increase in viral load in a couple guys, suggesting that the shock part worked. It was a bit surprising. It didn't actually follow what we had predicted, so it may be one of these maybe a false path. We're not sure, but we have just finished a 30-patient study with lots of support from amfAR to ask the question. So that's shock. What about kill? Okay, you get the virus out, the cell may or may not die, probably won't die. We're going to have to actually aggressively now kill it. And how are we going to do that? I think if I were to bet on one intervention out there that's going to be widely applicable in a cure arena, it is this remarkable vaccine that has been developed in which Louis Picker and his team have taken CMV. CMV is a virus that probably 2/3 of us in this room have. It's very common. It doesn't have any obvious effects on health, controversial, but no obvious effects on health if you have a normal immune system. It has this amazing capacity to manipulate the immune system to its own advantage. Louis Picker and colleagues took advantage of this and took the CMV, put some HIV stuff in there, SIV as well, put it in some monkeys, and CMV then turned on the immune system in this rip-roaring way to make all these SIV, HIV-specific T cells. And what Louis and Picker did is they took monkeys who had gotten this vaccine, infected them, and they were infected, and surprisingly, they became cured. So, and that no one actually really thought that was going to be possible, short of a bone marrow transplant, to actually cure with an immune system this type of infection. Never been done before. So a lot of interest in this approach, lots of interest in other approaches, including, and this has been really actually remarkable. So HIV has generally been an area where there's always been these huge arenas that don't talk to each other. There's prevention, there's microbicides, there's vaccines, there's treatment, there's epidemiology. But the vaccine world and the cure world have really begun to merge with that CMV vaccine and also with this concept of these neutralizing antibodies. The vaccinologists out there have identified, now dozens, I believe, of antibodies that come naturally in people with HIV that are broad and powerful and potent. Antibodies can seek out throughout the body, everywhere except perhaps the brain, and that's why Paul's work is so important. But anyway, it can grow out throughout the body and identify and tag things like HIV. And if it's tagged, then the rest of the immune system can actually kill that source. So these antibodies, which the vaccine people have found, are now being actually quickly repurposed for cure, and there's actually studies going on now to see if it'll work. So that's the shock and kill approach. There is a whole other family of approaches I'm not going to go into that get at the fact that HIV has a permanent, probably irreversible effect on the immune system that is hard to rebuild, and you end up with this inflammatory environment, even during therapy, that is actually probably contributing to the ability of the virus to persist. Lots of reasons for this. Huge amount of interest going on trying to figure out why this is happening, what the effects are. But it has led to a number of testable hypotheses that the inflammatory environment that exists in people with therapy can be reversed, perhaps making them healthier, but also contributing to a cure. And there's just a couple of ideas here that are actually now moving into first in testing human clinical trials. I'm just throwing this out there, just to give you an idea of the broad range of approaches that are being taken in terms of modifying and manipulate the immune system, including using anti-PD-1. Now, I'm not going to get into the details of this, but the cancer world has been completely taken over by the exciting data that if you block PD-1, which turns off T cells, if you block PD-1, you can turn on T cells and kill cancer cells. And this is changing cancer on a day-to-day basis right now. It's the most exciting thing that's ever happened in the cancer arena. We think if you block T cells with a PD-1 antibody, you may actually be able to help clear HIV. And those studies are ongoing. And probably the best proof, I think, that by modifying what the environment of the immune system looks like might actually help is the so-called Visconti Cohort. This is 15 or so people in France who went on therapy really early, stayed on it for years. Their immune system looked great, had very little inflammation, stopped drugs, and the virus has not rebounded. Still not entirely sure what's happening there. Not 100% of people agree that this is actually a real phenomenon, but it is actually stimulating a lot of interest in ways to make the immune system healthier so that we can cure people. Finally, what about cell and gene therapy? Now that we could talk all day about this stuff. The greatest impetus for this type of work, of course, is the Berlin patient, Timothy Brown. What was not mentioned today, but should have been, is that, when this study was done several years ago, and Timothy was taken off drugs, the virus did not rebound. That did not mean that he'd been completely cured. So Timothy showed up in San Francisco, and just a wonderful, charming man. He knew that he was a very important person in terms of stimulating HIV research. And this is Timothy and his doctor who came up with the idea. So through I think actually one of the first ARCH grants that I was aware of from amfAR, we talked to Timothy. We brought him in. We said, Timothy, we don't know if you have any virus left. We'd like to find out. And in order to do that, we need to do leukapheresis a couple times, if you don't mind. We need to do a rectal biopsy. We'd like to send you to Minnesota to do a colon biopsy. And while you're there, by the way, we'll take out a lymph node or two. And we'd like to do a lumbar puncture and see what you have in your brain. And Timothy said, sure, doc, go for it. Never complained. And with a network that was built through ARCH with a lot of amfAR funding, specimens were sent throughout the world from Timothy. And we all concluded at the end of the day that he was, in fact, truly cured, that there's no virus left. Proving a negative is not the easiest thing in the world, but we're all comfortable making that conclusion. And this is stimulating lots of research in gene therapy, as are the Boston patients. Tim is a modest man and didn't really talk about how it has his work has not only stimulated interest in gene therapy and stem cell therapy, but he's uncovered through this work of these Boston patients this idea that certain types of cells, natural killer cells, actually may be really important in clearing the virus. And as a consequence of that finding, we are moving ahead with other types of studies to take a look at it. So curing HIV is ambitious, and it's not going to be easy. And we have made certain advances. We've had major drawbacks, but we've learned from each of those. But I think it's feasible. Most people do agree now that it's actually feasible to cure this infection. The way we're going to do that is we need funding that I believe is nimble. This is a rapidly moving area. We need foundations. The NIH and other government agencies are not necessarily as nimble to be able to quickly move as the field moves because of the way that they're structured. But amfAR has proven over and over again that it can actually identify hot areas and quickly give the infusion of funds that are necessary. It has to be high risk, goal-oriented, work that has to be multidisciplinary and often international, as supported by the ARCH collaborations, are perfect examples of that. We do need, I think, a way to basically bring academia and particularly biotech pharma more into these types of collaborations. And we need long-term commitment. One of the problems with the way funding is right these days is that you get fundings for 2, 3, 4, or 5 years, and this is it's going to take more than 3 to 5 years to figure this out. Thank you very much.